This is the answer key for the last test I gave on equilibria. The first question is calculate the pH of a 0.85 molar acetic acid with a Ka of 1.8 times 10 to the minus 5. Then calculate the pH if 25.82 grams of sodium acetate is added to the solution. The volume is assumed to be 500 ml. The first thing I did was to show the equilibrium of the acetate, of the acetic acid dissociating into acetate and the hydrogen ion, and the pH is calculated using the iterative method where I set up an equilibrium where the concentrations of acetate and hydrogen ion are set as X. The concentration of the acetic acid is 0.85 minus X after a certain amount dissociates, so that equilibrium 1.8 times 10 to the minus 5 is equal to X squared over 0.85 minus X, and I used the iterative method to calculate it. I first assumed that the value of X was going to be so small that it would leave this unaffected, so I calculated 0.85 as the denominator here. Once I got the preliminary value, X sub 1, I replugged it back into the main equation, to the original equation, to find out what the denominator was with X subtracted, and then solved again for X. And I did that a couple times until the number became steady and stopped changing. That gives you the same result as if you'd plugged it into the quadratic formula. It's called the iterative method. So the concentration at equilibrium for H plus turns out to be 3.9 times 10 to the minus 3. We plug that into the pH equation and we get a pH of 2.41 when we account for significant figures. And then what we do is we add the acetate, the sodium acetate. We add 25.2 grams of sodium acetate. And here I calculate how much sodium acetate that is. That's the molar mass of sodium acetate, which I calculated over here. Here's the mass of sodium, mass of carbon times 2, a mass of hydrogen, a mass of oxygen times 2. So we have 0.303 moles of sodium acetate. It's in a 500 ml solution, which is half a liter, so the concentration turns out to be 0.606 for the acetate anion. And then what we do is we use the Henderson-Hasselbalch equation to calculate the pH. We have to find out pKa using the value of Ka, which is 1.8 times 10 to the minus 5. And where did we do that? I think I may have not included that in the calculation. Oh, here it is. pK is equal to negative log of Ka, negative log of 1.8 times 10 to the minus 5. There's the pKa value. Then we plug it into the Henderson-Hasselbalch equation. Here's the concentration of acetate anion. Here's the concentration of the acetic acid. And at equilibrium we get a pH of 4.6. So it creates a buffer system, and the pH is buffered at 4.6. So we see as a final answer that I wrote, before the addition of sodium acetate the pH is 2.41. After the addition of 25.2 grams of sodium acetate, a buffer is made with a pH of 4.6. On to the second question. A buffer contains 0.12 moles of propionic acid and 0.1 moles of sodium propionate in 1.5 liters. A. What is the pH? B. What is the pH after the addition of 0.02 moles of potassium hydroxide? So again, we show the equilibrium equation, which shows propionic acid dissociating into propionate and a proton. We show the initial conditions. And I used an IRAC table for this one because I wanted to show how you can calculate the concentrations in the last step by including the volume of the solution. This 0.02 symbolizes the amount of propionic acid that is consumed by the addition of sodium hydroxide. So it's a strong base being added. It consumes as many moles of the weak acid as there are moles of the base, and there are 0.02 moles of base being added. So that's why we're getting this number minus 0.02. Here this plus 0.02 symbolizes the fact that as the propionic acid is deprotonated, it generates the same amount of propionate anion, which I symbolize this PR minus over here, and the propionic acid is symbolized as HPR. We then calculate the equilibrium concentrations by dividing by the volume of the solution. We also calculate the initial conditions before the addition of base. The propionate concentration was 6.6 times 10 to the minus 2, and the propionic acid concentration was 8.0 times 10 to the minus 2. We then find the pKa of propionic acid by inserting it into the negative log of Ka, and that turns out to be 4.88. We plug those numbers all into the Henderson-Hasselbalch equation to find a pH of 4.81. That is before reaction with the base. After the addition of base, we again use the Henderson-Hasselbalch equation, and we plug in the equilibrium concentrations, which have now flipped to what they were before the addition of hydroxide, and that has the effect of raising the pH to 4.97. Question 3. We're asked to calculate the solubility of ferrous hydroxide when buffered at the following pHs: 7, 10, and 12. So the first step in solving this is to find out what the pOH is. The pH is 7 in the first instance, so 14 minus 7 gives you a pOH of 7, and from the pOH we can calculate the OH minus concentration, which is 1.0 times 10 to the minus 7. We then plug it into the KSP equation for this substance. Notice that the ferrous ion concentration times the hydroxide ion concentration squared gives you the value of KSP, and the value of KSP is 7.9 times 10 to the minus 16. So KSP is a constant, and the OH minus concentration is fixed by the fact of the pH being given to us. So the only variable here is the iron, the ferrous ion concentration. And we'll notice that as the pH becomes more and more basic, that the ferrous ion concentration drops each time. So in the first instance it's 7.9 times 10 to the minus 2. In the second it's 7.9 times 10 to the minus 8, and in the third instance it's 7.9 times 10 to the minus 12 at pOHs of 7, 4, and 2. Remember, the pOH is always found by subtracting from the pH from 14. So if the pH is, say, 6, then the pOH is going to be 8. Last question, number 4. It says, what is the pH of a solution made by mixing 0.3 moles of NaOH, 0.25 moles of sodium, disodium monohydrogen phosphate, and 0.2 moles of phosphoric acid with water and diluting it to 1 liter? And I supplied the Ka values for the 3 dissociations of the phosphoric acid. And I comment here that this mixture sets up a buffer system. The addition of hydroxide constitutes a partial titration. The first proton is used up by the amount of base added, and the second proton is partly used up. The equilibrium so established occurs between dihydrogen phosphate and monohydrogen phosphate, which are principal species left when the hydroxide is finished. So we show the first dissociation of phosphoric acid into dihydrogen phosphate plus a proton, and we show the initial amounts 0.2 and 0 before the dissociation, and when we add the base, the strong base, it uses up the same amount of phosphoric acid, so that the phosphoric acid is now gone down to 0, and the dihydrogen phosphate has increased to 0.2. But now we still have 0.1 mole of sodium hydroxide left over. So we set up another IRAC table where we use the second dissociation to titrate the remaining base. So that goes from 0.2 to 0.1, or minus 0.1 gives us 0.1 left over, and because the solution's final volume is 1 liter, the concentration is 0.1 molar of the dihydrogen phosphate. With the monohydrogen phosphate, which was already at 0.25 because it was added in at the beginning, we're told 0.2 moles of disodium hydrogen phosphate, plus the 0.1 that's left over from the NaOH reacting. Remember that the NaOH is not completely finished, so that 0.1 the 0.1 moles of dihydrogen phosphate that gets used up generates 0.1 mole of hydrogen phosphate. So now the total concentration is going to be 0.35 for the monohydrogen phosphate. Then we use the Henderson-Hasselbalch equation, plugging in the values of monohydrogen phosphate and dihydrogen phosphate concentration. We find the pKa for that Ka sub 2 by taking the negative log of the Ka sub 2, and when we plug in all the numbers, we find that the pH works out to 7.75. The red arrows, of course, symbolize what I'm looking for when I'm marking the test. The 4 questions are out of 36, 24, 39, and 34 respectively, for a total of 133 points.